Here's another episode of Rust in Production, a podcast about companies who use Rust to shape the future of infrastructure. My name is Matthias Endler from Corrode, and today we talk to Richard Feldman from Rock about their reasons for migrating from Rust to Zig. Richard, thanks so much for taking the time for the interview. Can you say a few words about yourself and about Rock, the programming language you're working on?
Yeah, sure. So I'm Richard. So my day job is I work at Zed Industries, making the Zed code editor, which is all written in Rust. So mostly what I spend my time on is writing Rust. On the side, I have been developing for the past several years the Rock programming language, which I created, but I work on with a number of other people. Originally, Rock's compiler was written in Rust completely, and now it's being rewritten in Zig, which is what I assume we're going to talk about.
Precisely. Yeah, it's perfect. We had said in a previous episode as well, if you want to check that out, we will link it in the show notes. That was an amazing episode as well. And also for this one, I have really high hopes because your name was mentioned a couple times by a couple of our listeners because you wrote an article, or maybe you published a post, let's say, about your migration from Rust to Zig. But before we get into that, what is Rock? What makes it special? Why did you start that project?
Yeah, so Rock's tagline is fast, friendly, functional, and basically it's a functional programming language. The goal is to be really, really fast. We want it to be the fastest garbage collected language. That's sort of the goalpost that we set. So I would say that Go right now, as far as I'm aware, is the fastest garbage collected language, and we want to be faster than Go, not as fast as Rust or C++ or Zig or any of those, because we want to be completely memory safe, guaranteed. And basically the goal is to be competing with languages like Go, or maybe like, OCaml also has a good reputation for speed, while being a functional programming language, as opposed to like Go being very imperative. So yeah, that's the goal in terms of speed. In terms of friendliness, it's like have really simple APIs, very, very heavily inspired by Elm. Rock is sort of an outgrowth of my really positive experiences with Elm, but Elm is targeted at compiling to JavaScript and front-end web development, whereas Rock compiles to machine code or to WebAssembly and is sort of trying to address all of these use cases that are not front-end web development. Also, Rock's design has evolved quite a bit from Elm's. Now it's a much different language. When it started out, it was very similar to Elm. Now it's a lot less similar, but I think the essence of that sort of ethos of simplicity and really nice APIs and really friendly compiler error messages and things like that. Actually, Elm's error messages inspired Rust, even though I think Rust is now more famous for compiler errors.
That's true.
So all of that is sort of what we're going for with Rock.
And take us back to the time when you started the project. What was the ecosystem like? What were some of the other languages that you got inspired by when you started with Rock? And also, what was that initial spark that told you, hey, I need to do this, and now is the best time for it?
Really, the inspiration for it came from an experience I had. This is back when I was working at NoRedInk. We had this huge Elm front end, and we had Ruby on Rails for the back end. The Rails had been at the back end for long before we started using Elm, and we were trying to move the back end to something more functional. And kind of what we discovered was that there was just really this missing piece in the ecosystem, or at least that was my perception of it. We ended up going with Haskell and trying to use Haskell in kind of an Elm-like way. But my feeling was what we really want is a functional language that's statically type checked with type inference, built around purity. So OCaml is a functional language, but it's really not like pure functions everywhere. It's sort of like pure functions are encouraged, but they're not really first class in OCaml. Same thing with F#. And basically what we ended up concluding was that it just doesn't exist. Like there is no Elm equivalent outside of the browser. And that was kind of the spark for me to go and do it. As far as what languages inspired it, really it was Elm plus like maybe little bits and pieces of other languages, but it's very primarily like, okay, how do I take this great experience we've had with Elm and translate it to other domains besides just the browser? And I didn't want to just do servers. The idea was, I've been using this phrase, the long tail of domains. Like basically, there's lots of different use cases out there. It's not just servers. There's command line apps. There's native graphical apps. There's microcontrollers, robotics. There's this very long tail of different things you can do with programming. And I wanted to see, could we bring an Elm-like experience to all those different domains in terms of being a very simple functional experience?
Yeah, and I could see a few ways how this could go, because the Rust compiler is not or the first version of it wasn't written in Rust because Rust didn't exist, obviously. It was written on OrCaml as well. And then you have Elm, which might be another way to implement a new language on top of. Or maybe there's a language that I don't know of that you could use. But why did you choose Rust, and which alternatives did you consider?
Yeah, also great question. So basically, the reason I chose Rust was that I wanted the compiler to be as fast as possible. And I was, to be totally honest, scared of trying to do it in a memory unsafe language based on past experiences I'd had with segmentation faults that I really struggled to debug and stuff like that. When I was very young, like middle school era, I got into C++ because I wanted to do game dev. And I have some scars from trying to do that and bumbling around and just making a huge mess for myself. And the pitch of Rust of being, hey, you can have this really, really high performance ceiling. In other words, there's no mandatory garbage collector. There's no, built-in boxing of things. You can be as fast as a C or C++ program, but you're going to have memory safety. You don't have to worry about seg faults and all these things that I had these bad experiences with in the past. That was the pitch that sort of sold me, because my thinking was, well, if I do the compiler in OCaml or Haskell or something like that, yeah, that's going to be a more familiar experience to me. But at some point, I'm going to reach this point where I'm like, I want it to go faster, and I can't because I'm limited by the performance ceiling of this language. I don't want that. And then at that point, I'm like, what am I going to do? I'm going to say, oh, now I rewrite it in Rust. This is something that's happening in the JavaScript ecosystem a lot, is that a lot of projects started off being written in JavaScript because that's what was familiar to people. And then they realized past a certain point that a compiler is one of those use cases where just more performance is better. It's not like you get down to this point, in a lot of graphical applications, it's kind of like, well, as long as you're not dropping frames, as long as you're under the, however many milliseconds you have within each frame, humans can't perceive a difference. It's like, it's fast enough. And if you make it faster, nobody notices. Compilers are not like that. Faster is pretty much always better. It's just a big part of the UX is, how long are you waiting for rebuilds and stuff like that? And so my feeling was, especially actually this came up in Elm. When we were using Elm at NoRedInk, at some point we became the largest Elm code base. We had a couple 100,000 lines. I don't remember exactly how big it was at the time, but Elm 0.18, we were really feeling the pain of compile times. It's like we'd had a really positive experience and it was becoming a very negative experience just because we were waiting so long for rebuilds. And then when Elm 0.19 came out, Evan had rewritten a huge amount of the Elm compiler, which was written in Haskell, for performance. And it took him a long time. It's months and months and months. But when it came out, it was just this amazing breath of fresh air. All of our builds were fast again, like they used to be when our code base was small. And that was a really important lesson for me was, yeah, take the stuff seriously. Like compile times are a really big deal. And if you want to build a language that has a good end user experience, fast, friendly, functional, part of that friendliness and user friendliness is committing to having a compiler that is really, really, really fast. And that's something that I've been completely unwilling to compromise on since the beginning of the project. The compiler's always got to be really fast.
Yeah. And that was in 2019. Correct me if I'm wrong here. What was your level of Rust experience when you started with implementing Rock? Was it your first big Rust project?
It was my first big Rust project. So previously in 2017, I had dabbled in Rust, I would say. I'd written the Elm test runner originally in Node.js, and it was honestly out of frustration with the Node.js ecosystem that I was like, I just want to try something else. Why don't I try Rust? I never actually shipped anything out of that project. It was like I just started rewriting it in Rust, so I kind of got a feel for it. And the experience that I had initially with Rust was positive enough that I was like, yeah, this seems like something I'm willing to commit to for this compiler, even though I know this is going to be a very, very long, project that I'm going to spend way more time on than this little sort of side project thing that was just kind of for fun. I mean, my feeling going into this was that this is a language that I'm planning on putting multiple decades of my life into. And so committing to Rust with, just that minimal level of experience was a bit of a leap of faith in the sense that I didn't have enough Rust experience to know that I was going to like it that much long term. But at the same time, I had enough experience, it wasn't zero. It wasn't like I was sitting down and writing Hello World in Rust. And then I was like, that's what this compiler is going to be in. So I would say it was an informed decision, but my Rust experience at that point was pretty minimal.
When you think in decades, how does that shape the decision-making process?
I would say the main thing is that it gives me the comfort to make long-term investments. So a lot of projects that I've worked on in my career have been for startups. And startups are often like, yep, in 18 months, we're going to be out of money and disappeared off the face of the planet. So it's really important that we survive the next 18 months. And so making a long-term investment has to be balanced against, okay, if we make this long-term investment, is that investment going to cause us to not exist long enough to reap the benefits of the long-term investment? And there's always that constant tension. With this project, my feeling was the opposite. It's like, I'm very comfortable making long-term investments. The main thing I was actually thinking about was, and this is again shaped by my early experiences with Elm and participating in having the good fortune to live in the same city as Evan Czaplicki, who created Elm, and being able to talk to him about these things. But basically understanding that if I'm going to be making a long-term investment in the language, it's important that I also communicate that clearly and set expectations clearly to people who are using the language. So from the very beginning, I've tried really hard to communicate, hey, things are not set in stone here. We're going to be making breaking changes to this language, etc. The strongest way that I've done that is we intentionally, even though, like you said, the first line of code was 2019. I actually started designing it in 2018. But ever since then, we still do not have a numbered release. We're planning on having our first numbered release in 2026, like 0.1.0. But the whole reason we've been doing that is just to communicate, you have to build from nightly, expect things to break. Despite this, we still do actually have one person who's been consistently using Rock in production at his job. But that's, to me, an appropriate level of cautiousness, where like we only have one person doing it, even though lots of people have done Rock for hobby projects and stuff, because we are making big changes. And so those are all things that I see as long-term investments. I think if I were thinking more short-term, I might be like, okay, no, we already need to be backwards compatible. We can't, new releases need to not break things. Rust and Gleam and Go are all languages that I think went 1.0 and had a strong backwards compatibility guarantee relatively early on. And I think that really helped them with adoption. But to me, my goal is not immediate term adoption. I'm more thinking about what we're trying to do is really ambitious. And I really, really, really want to get it right, or at least as close to right as we can get it before we make commitments to backwards compatibility. So that's the type of thing that I think thinking in decades has as a benefit. It's that I can say, yeah, we've been working on this for years, but we still don't have a numbered release because I really want to clearly communicate to people things are going to break. Please don't expect that we're going to have backwards compatibility because we're not ready for that yet. But I think we're actually almost to the point where we are ready for that, which is pretty exciting milestone to be coming up on, hopefully next year.
If you want to learn Rust on a deeper level and really get your hands dirty with challenging problems while having fun and seeing your progress at the same time, I recommend checking out Codecrafters. I personally use it often to sharpen my skills and would recommend it to anyone who wants to become a better software engineer with Rust, or any other language for that matter. The challenges range from building your own shell to implementing Redis and SQLite, all the way to Kafka and DNS. This is perfect hands-on experience for backend engineers and systems programmers. And if you go to corrode.dev/codecrafters, you can try Codecrafters for free today and get 40% off when you upgrade to a paid plan. Head over to corrode.dev/codecrafters or click on the link in the show notes to get started today. I want to talk about Rust, the good parts, for a moment, because not everything was bad, I'm assuming. And in your post, you already mentioned a couple of really sane reasons to move away from Rust. But can you talk to us a little bit about the good parts, the things that you like about Rust, working with larger code bases, and what does it really feel like to work in the trenches with such a language?
Yeah, there are lots of good parts to Rust. And to be clear, I like Rust overall as a language. I'm not like a Rust hater. I'm not like, oh, Rust is, old and busted and Zig is like the new hotness. It's very much the opposite. It's more that for this particular project, I ended up deciding that, if we're going to do a rewrite anyway, then that rewrite should be in Zig rather than rewriting it again in Rust, which we'll get to. But Rust, the good parts. So, I mean, the first thing that I would mention is that, like I said, I work at Zed full time, and I don't think it would make any sense for Zed to move away from Rust. Like, Rust seems like it just fits the way that Zed's code base works like a glove. If you wanted to rewrite Zed in something other than Rust, first of all, that sounds like a really daunting proposition, not just because it's a lot of work, but because Zed's code base very, very heavily relies on a combination of features that Rust is really good at, such as, you have the memory safety, which when you have a wide contributor base, we have, Zed's open source. So it's not just that we have people at Zed working on Zed, but also we get all sorts of outside contributions. It's really helpful in that context to be able to look at someone's pull request and be able to say with a lot of confidence, okay, this is not introducing sneaky memory safety bugs. Now, granted, you can make the point that, lots of non-memory safe languages have lots of contributors too, like Zig, for example. Also, Ghosty, which Mitchell Hashimoto made in Zig, has lots of contributors. But I think it's definitely a selling point of Rust that when I look at a pull request coming into Zed, I can say with a lot of confidence, this is not going to introduce some very subtle memory safety bug that I'm going to have a really difficult time debugging later. Sort of the blast radius of what a new contribution can do in terms of mistakes is a lot smaller. And I do think that's something we benefited from in the Rust version of the Rock compiler as well. So outside contributors, but also, of course, within the code base, it's the same thing. It's definitely a benefit to not have to worry about those things. I wouldn't say I've gotten zero segmentation faults or memory safety errors in either the original Rust compiler for Rock or in Zed. Actually, literally yesterday we had a seg fault in CI, and it was in our new Windows code base, and some of the stuff that we're doing is very low level, interacting directly with the operating system, graphics APIs and drivers and stuff like that, because it's a very high performance code base. And Zed is a good example of the classic Rust model of if you're going to have some unsafe code because you're doing just innately unsafe things, maybe for performance, maybe for FFI, whatever, just having it very small and contained is helpful. And so, it is helpful to know that the surface area of that is smaller and more contained. And if you look at Zed's code base, I think you see what you want to see in a classic Rust code base, which is the amount of unsafe is a very, very small percentage of the overall code base. So yeah, I think all of those things are great. Obviously, the cargo ecosystem is very large, and there's lots of stuff you can get off the shelf, which is nice. There's this classic problem in a language where if you were to time travel back to when Rust 1.0 came out, or even before that, everybody would say, well, ecosystem is a downside of Rust. Where they would say, like, well, there's no ecosystem. How can you ignore the gigantic C and C++ ecosystem? Whereas, of course, now ecosystem is the selling point. I don't know how people have amnesia about this, but it's like every language that has a big ecosystem today used to have no ecosystem. It just grew over time. That's a normal part of a language growing. So it's totally reasonable for people to say, I don't want to use this language right now because right now the ecosystem is small. But it's a little bit of a pet peeve of mine when people act like that's just this permanent state. It's like, no, actually, it's the opposite of that. It always, the ecosystem always grows. That's where all the ecosystems you think of as big came from. But certainly at this point, the crates.io ecosystem is just, very large, and you can pull all sorts of stuff off the shelf. And that's a selling point. There are some things in Zig that we use at Zed that we couldn't get off the shelf in Zig. We would have to do FFI to a C library or a C++, and C++. If you're trying to pull stuff off the shelf in C++ and use that in Zig, that's a much bigger pain than trying to pull something off the shelf in C and use that. C is just a lot easier to interoperate with in Zig. So yeah, the ecosystem also a selling point. And I think the biggest thing for Zed's code base is just the fact that you have, for lack of a better term, drop. And because you have drop, you have reference counting, automatic reference counting. And we use Arc all over the Zed code base. It's just everywhere. And we rely on it very heavily. We're constantly cloning Arc things. When I first got to the Zed code base, I was a little bit nervous because I would see these .clones everywhere. And my experience from writing the Rock compiler in Rust, which used very little Arc or RC, was that, if I see a .clone, that's a hot spot. That's a big performance potential problem. And we had this convention of in the few places where we would use Arc, we would do the Arc : clone. So it's really clear, don't worry, it's okay. It's just a, it's just a reference count bump. We're not deep cloning the whole thing. But in Zed's code base, if you did that, you would be writing Arc : clone so many times. It would just be everywhere. So what happens instead is you just use .clone because that's way more concise, because that's the normal way that cloning is used in the Zed code base. But to do that, you do have to have that, drop, basically. You need to be able to have automatic, C++, people would call it RAII. Zig by design does not have that. And so that's one of the examples of why the idea of rewriting Zed's code base in Zig sounds totally ridiculous to me. It would just be a terrible choice because, some projects, one language is a good fit for them, and then other projects, another language is a better fit for them. So I'm comfortable making the claim that I am happy writing Rust at Zed as my day job, and I think that's the correct choice for Zed. And also, outside of work, having the Rock compiler be in Zig, and I think that's the right choice for Rock compiler. So different projects, different needs.
That thing that you mentioned with arc clone and making that explicit, I really like that idea. That's such a great idea because, you show that the cost of cloning is really low. And of course, you couldn't do that in all places where you had a lot of usages of arc, but I wondered if you could build a trade extension for that and you had a arc_clone method on the type that was arc, for example. And then it would be kind of, explicit, but also weirdly strange. So I'm not 100% sure if you want to go down that route. But
we're probably not going to do that in Zed because, the number of places we would have to switch to that is extremely high. But yeah, you could call it bump or something. Like you're just bumping the reference count. That's actually a really cool idea. I never thought of that.
Yeah, nice. So you wrote a lot of Rust code, probably many tens of thousands, maybe hundreds of thousands, maybe millions of lines of code by now. I don't know.
Probably hundreds of thousands. I don't think millions. I think I'm under 1 million probably. So yeah, the Rock compiler at the point where we decided to switch over and do the rewrite was at like 300,000 lines of Rust code. Now I did not write all 300,000 lines. There's a lot of other contributors involved in that for sure. But at the same time, I also wrote a lot of lines that ended up getting deleted or rewritten, etc. So I think between that and my work at Zed, I'm definitely sure it's multiple hundreds of thousands of Rust code. I also taught a course on Rust. I taught Intro to Rust for frontendmasters.com. So that was like an 8-hour, course just teaching people Rust from scratch. I've not taught a Zig course there. I did teach a C course, but yeah. So I have a lot of experience hands-on in Rust, a lot of hours with it, and also I've taught it to beginners, which always requires, learning a little bit of extra detail about things where you sort of have these gaps. And as soon as you have to explain it to someone in depth where they need to understand it, you sort of immediately realize where the gaps are and kind of have to go fill some of them in. So yeah, I definitely feel comfortable saying I feel like a Rust expert, but not a Zig expert yet. I don't think. I've had a lot less time with Zig.
Because that kind of leads me to the next question, which is, with that level of experience, some patterns more or less naturally must have evolved. And there are probably things that you would call idiomatic Rust that maybe are not written down anywhere or maybe are not in the book. What would you say are some things that you would consider ergonomic or rustic code? How does it look like? What is it like in practice?
Yeah, well, the first thing is, of course, use unsafe as little as possible, ideally not at all, if you can avoid it. I guess there's a lot of using traits for things. So, for example, if you can initialize something, you probably want to use from and into. Like that's a kind of a standard practice in the ecosystem, just so you can make the conversions a little bit more ergonomic. Similarly, if you're going to be, formatting it as a string, then okay, maybe you want to, give it display. You probably want to give it debug. Like I think there's a lot of trait-centric thinking when I'm writing Rust code, like in terms of like what traits do I want to implement, even just the baseline, like don't write standalone functions in the top level of your module. Prefer to make an impl for the particular type and then, add it to there, unless you're writing some function that's really not tied to any one particular type. Kind of the default is to think in terms of types and in terms of traits, and then in terms of impl and putting things on there. Also, like pretty straightforward, to think about doing like taking references to things. So like, ampersand or ampersand mutt. I say mutt. People at Zed usually say mute, but I don't know. I've always said mutt. So no, I since my first experience writing Rust was with other people who, were doing Rust for the first time, we kind of developed our own like terminology, I guess, or way of pronouncing things. And when you're looking at other people's code, you don't see how they pronounce it. But at Zed, we pair program a lot. I think I'm the only one who says mutt. Everybody else says mute, but it's fine. Which makes sense. It's mutable. But anyway, so I think another sort of unwritten rule is that you really should try to avoid putting references in data structures, which is to say you should really try to avoid having lifetime type parameters in your structs or what have you. This is something that in the Rock code base, like the original one, we did not really do. So we kind of took the approach of, well, yeah, I mean, we don't want to have allocations for these things. So let's use Bumpalo for all of our arena allocations and then store references to either stuff on the arena or stuff. I guess, yeah, it always ended up being in the arena. It wasn't really on the stack because then the lifetimes wouldn't work out. But yeah, so that's another, I don't know, unwritten rule, I guess, is, and it's not the type of thing where you necessarily need a rule, because as we discovered, if you do that, the ergonomics end up being pretty annoying because you have this like tick A that's just following you around. Everything you write, tick A, tick A, tick A, tick A everywhere.
Yeah.
So I would say it's not that you can't do that in Rust, but rather that, you're asking like, what's idiomatic? I think that's something that people tend to avoid, is having lifetime annotations be everywhere. It's more like, if you're going to have lifetime annotations, you kind of ideally want them to just be confined to a function signature rather than sort of leaking out into your data structures. And that's kind of, I guess a lot of people will solve that by using like reference counting or things like that, or interior mutability or something like that. Of course, at that point, as soon as you get into like cell and things like that, it's sort of like, well, if you make a mistake, then now you're potentially, dealing with a runtime panic, which is not great, or else having to do all these conditional things. So yeah, we did a lot of that, and I think kind of learned the hard way that that's something that you should probably avoid when you're writing Rust code, is having lifetime annotations in your structs, like your data structures. What else? Yeah, I mean, I guess in general, try to avoid boxing and, doing things on the heap. But I would say Rust is less hardcore about avoiding those things than something like C or Zig is. So if you look at like the lowest level C operating system APIs, C really, really, like, the operating system is really not going to be calling malloc for you, like, almost ever. It's really going to be a lot more doing things like, okay, you need to pass in what in Rust would be the equivalent of like a mutable reference to something, where you're saying like, give me a pointer to this data that you've already pre-initialized, and also tell me how much, how many bytes I have to work with, and I'm going to write into there. Like the caller says, here's some memory that I've, in Rust, this would be like maybe uninit, basically. And it's like, hey, give me some data. I'm going to, write to it, and then I'm going to give it back to you. I'm going to return back to you. And don't worry, the data has been written there. And I'll tell you how many bytes I wrote into there. That's a really common idiom that you see in C, at least in like low level operating system type code. Whereas in Rust, it would tend to be the opposite. It would be more like, no, don't worry, I'm just going to take care of that for you. There might be some API that's like, give me a mutable reference to something and I'll write into it, but that's a lot less common in Rust. So there's a pro and con there. On the one hand, the APIs in Rust tend to be nicer looking, I would say. They look a little bit more, dare I say, functional in some cases, where you're like, I'm going to call this, it's going to do some heap allocation with the global allocator, and then return, a string or a vec or whatever. Whereas in C, it's more like, yeah, give me a buffer. And it's like, well, what if the buffer's not big enough? It's like, well, then you're probably going to have to call me again, and I'll fill in the rest of the buffer after you resize it for me, or something like that. So you don't tend to see that type of thing in Rust. It tends to be more open to doing silent allocations than C or Zig.
Now, from experience, I know that quite a few people that I would deem to be experts in Rust or very experienced are pretty lightweight on design patterns for some reason. And I wonder if you also saw that in working with larger code bases, and where you stand on that side of the spectrum. So do you use a lot of design patterns in your code, or are you also just like leaning into what you mentioned, structs, traits, and combining those? And do the design patterns evolve more or less naturally for you, or is it something that you consciously think about when you write code?
So let's be a little bit more specific. When you say design patterns, are you thinking about sort of the concept, as in like, patterns of design that come up, like, techniques and things like that? I mean, of course, in that sense, like, I would just call those, I don't know, idioms or something like that. Usually when I think design patterns, I'm thinking like gang of four, observer pattern, things like that, visitor pattern and whatnot.
Yeah.
So certainly I'm not thinking in terms of gang of four stuff. Like, I did a lot of enterprise Java early on in my career, and that, based on that experience, I've kind of, I don't know, sampled the object-oriented style, and I've sampled the functional style, and I've sampled the imperative procedural, not object-oriented style, which is what I would put Rust and Zig in that category. And my conclusion is that imperative procedural is fine, functional is fine, object-oriented is a mistake. I've been trying to sugarcoat that more and more over the years, trying to be diplomatic about it, but for the purposes of this podcast, I'm just going to say, yeah, I don't think any of that was the right direction. I think it's going to turn out to be a dead end in programming that people are going to look back on as like, that was a thing that people used to do. I don't think that's the future of programming. So yeah, I'm happy to have moved past that.
Oh, that's interesting, because you use different ways to encapsulate code. Then you use namespaces and modules and freestanding functions to group that logic. But don't you still need some way to hold state, like structs or things where you can maintain some sort of order of the events that come in, like as in an actor system or so? Like it's kind of a pretty bold statement to say, oh, P was a mistake. What's the alternative then?
Well, it depends on who you ask, right? So if you talk to some of the like Casey Muratori and Jonathan Blow and people like them who do a lot of like high performance game dev, saying, oh, it was a mistake, is they're just like, yeah, so let's talk about something interesting. Like we've known this for a very long time. Yes, in the broader programming world, I agree that it's a bold statement, but there are quite a lot of people who are just like, yeah, of course, it's not controversial at all. So yeah, I mean, like you mentioned, encapsulation. So for example, encapsulation is a special case of modularity. So modularity is the idea of the boundary. It's like saying it's just pub and private, right? Public and private interfaces. So you can say like, here are the things that I'm exposing. Here are the things that I'm intentionally not exposing. Nobody outside my module can access my private things. Encapsulation just means modularity, but in an object-oriented context. It's like modularity applied to classes and objects. Well, if you don't have classes and objects and you just got, like you said, structs in Rust, like modularity is fine. You can, all we're talking about there is just like, did I decide to make this field on my struct pub or not? Right? Everything just sort of follows from that. It's the very basic thing of saying I'm intentionally hiding these implementation details. And the reason that I'm hiding these implementation details is that, for example, I'm trying to create an invariant that I want to be enforced by the compiler. Like I want to make sure that nobody is, reaching in and messing with these internals, because if they did, it would violate my assumptions. And I want to really hardcore communicate that by giving anyone who tries to do that a compiler error. Or I might be making a library and I might want to say, I want to have really strong backwards compatibility guarantees, but I might want to change the internal structure of this. Same thing, right? I'm going to make these things pub and these things private. That's all it is. That's modularity. And then encapsulation is just modularity, but I'm specifically talking about modularity at the level of a class. And since Rust doesn't have classes, I would argue that technically speaking, Rust doesn't have encapsulation. Rust just has modularity. Somebody might, but people use these terms pretty interchangeably. I think in a lot of cases, like a lot of people, well, first of all, even though the term modularity, I think, might have come first. I don't know. Now we're getting back into like Alan Kay coined the term object-oriented in the 70s. And, Nicholas Wirth was working on Modula, or also in the 70s. I'm not sure exactly which term technically came first, but certainly the term encapsulation is more popular today. So I think that's what more people associate with that boundary system. But I think it's worth noting that from a historical perspective, modularity is the thing that everybody seems to agree that they want now. Like literally right now, I think on Hacker News yesterday or the day before, there was a front page article about modules in C++ and like when are they coming? So an observation I would make is that every language that just had encapsulation, which is to say the only way to do public and private was at the class boundary, every single one of them has ended up wanting a module system. Every popular one. Okay, like I'm sure there's some, obscure languages that don't have it. I'm sure Smalltalk will never, consider adding a module system. But I mean, C++, Java, right? Like all these languages have ended up having some separate mechanism. So it's like, actually, we don't want only to be able to do that through classes. And that makes sense. Modules are a really nice idea. But the question becomes, if you have public and private at the module level, do you also need a separate class thing, which also has its own public and private, or is module level sufficient? And it seems to me to be the case that module level turned out to be, sufficient. And, Rust is an example of a language that does not have objects, does not have classes, unless you want to count like, whatever, din objects, dyn, like trait objects and stuff like that. But that's just the name they chose for that. That's not like, they are not objects in the object-oriented sense. They don't have classes. They don't have inheritance or any of that stuff. So yeah, I don't know. I don't want to get too far in the weeds on that, but I guess to sum it up, I would say that, and actually I gave a whole talk on this. Well, I've given multiple talks on the subject of object orientation and whatnot, but I gave one called The Next Paradigm Shift in Programming, and also The Return of Procedural Programming. So The Return of Procedural Programming is a very on-the-nose talk about like OO got really big, and if you look at what are the biggest new languages that have come out that are getting popular, they break down into two categories. One is they're just a sort of plus plus version of an already popular language. So for example, Kotlin is basically Java plus plus. It's like they took Java and then intentionally have seamless Java interop. And so you could not possibly make a language that has seamless Java interop without having it be object oriented, because Java is extremely object oriented. But if you exclude those and say like languages that are not coupled to an existing already popular language, what are the greenfield languages like? And there's only two. There's Rust and there's Go. Those are the two languages that are getting popular, that are greenfield, not based on and coupled to an existing already popular language. And neither of them are object-oriented at all. They're just procedural languages. And that's hence the title of the talk, The Return of Procedural Programming. So if someone wants to make the case that object orientation is the future, you might want to ask, why is it that the only new popular object-oriented languages that are coming out and gaining actual traction in the real world, why are they all coupled to legacy object-oriented languages? And nobody's making new object-oriented languages from scratch that are seeing popularity.
I can get behind that. Never seen it this way, but the way you explained it makes a lot of sense. We will link those talks in the show notes. I guess Rust kind of found a nice balance there, because that's also somewhat what I consider idiomatic Rust, to make use of separate input blocks, to make use of composability with traits and so on. And you don't always need trait objects and that sort of thing. You can ensure a lot of things at compile time and make it still composable, right? And still have all the ways to do different kinds of visibility at your disposal. You can have pub, you can have pub crate, you can have public modules and so on. So that's pretty cool. I'm sure we could talk about this for a long time, but I would like to shift gears to the first time where you noticed that Rust might not have been the right choice for the language that you were building. What was the first time when you noticed, well, no, I need to think about an alternative to Rust?
That's very easy. We talked early on about how a big part of programming language UX is compile times. They got slow. When we had a small Rust code base, their compile times were fine. Everything was nice and snappy. And as it got bigger and bigger, they got slower and slower. And now they're just quite slow. I just did this morning, I did a scratch build of the Rust code base, and it took like 30, 40 seconds, somewhere in there. And a rebuild still took about 10 seconds. And in contrast, our Zig project, which granted, this is apples and oranges. The Rust code base is like 300,000 lines. The Zig rewrite is currently at about 100,000 lines. The scratch build of the Zig one was like 13 seconds or something like that. And then the incremental rebuild was like 1.3 seconds. Now, that's worth noting that that's going to get much, much faster in the future, because I'm working on an ARM64 Mac. Zig has an alternative backend to LLVM, but it's only x64 right now. The ARM one is still a work in progress. It hasn't shipped yet. It's not stable. And once it does, then that 1.3 second rebuild is going to get much smaller still. And also Zig still doesn't have they have not fully realized their goals in terms of incremental rebuilds, whereas Rust, I would say, has at this point, based on the constraints of the language, with crates being the smallest compilation unit rather than individual files. So given all of that, it's already the case that we're seeing a much bigger gap between Zig and Rust than sort of linear in terms of lines of code. Like, if all else being equal, Rust code base is 300,000 lines versus the Zig one being 100,000 lines, you would think that the Zig one would be maybe 3 times faster, but not 10 times faster for like incremental rebuilds. And also, it's not just that it's already 10 times faster, which it is. It's that, or it's 1/10 the compilation, incremental compilation time, but also that it's going to get much faster in an upcoming release, like probably the next one after the current release. Because when I'm assuming the ARM64 one's going to ship, and actually people who are working on the raw compiler in x64 processors are already benefiting from that much faster compilation time, because that one already has shipped. So meanwhile, like on the Rust side, I mean, LLVM is a very, very known culprit for making slow builds. And unfortunately, you can't just, do like check, like cargo check, that's not the whole thing. You want to run your tests. And in order to run your tests, you have to do code generation. And that requires LLVM in Rust. There is a crane lift backend, but I'm not kidding. When I started Rock, wrote the first lines of code, the crane lift backend for Rust was work in progress. It still hasn't landed. So that was 2019. And maybe it's right around the corner, but I can only hold my breath for so long.
Yeah. And I guess you probably used all the tricks at your disposal to make it faster. You probably went through a lot of tutorials and tried a few things. It's probably optimized to the max by now, the Rust code that is.
I wouldn't say we went all the way to the max. We certainly tried a lot of things. So like the really obvious one that everybody says, oh, just try mold. And said mold made no difference whatsoever for us. I mean, we didn't even bother enabling it on CI because we had people who were using like daily driving Linux. And we're like, oh, let's try it out. They're like, I mean, it's a little faster, like, mold for linking. We tried splitting up our crates along more boundaries, etc. I mean, really the overall feeling that we ended up having was that even if we do like use all the maximum number of tricks and try to like contort the code base around just the number one goal is trying to get it to build as fast as possible, it's just still not going to be anywhere near as fast as Zig is building. I mean, the Zig team is in the progress of working towards hot code reloading, where like you're running your Zig program, and while it's running, you make it, you save it and it's like instantly updated with the running program. That's it's inconceivable to me that Rust would ever have that like in my lifetime. I'm not saying it's impossible. I'm just saying that just based on the way things are organized right now. And I've talked with a lot of people in the Rust project about compile times. There are definitely some heroes who are like really trying to fight the good fight, and trying to make like compile times a major priority. But unfortunately, it feels like that's not the majority view right now. It's the majority view is not that compile times are a major priority or need to be a major priority, or maybe it's that people think that they should be a priority, but their ambitions for how much of an improvement they think are possible is way below what the ambition level is for Zig. Like when I talk to Rust core team members, and I've told them this, so this is not, I'm not, I'm not saying anything here that I haven't said to people who work on Rust. When I talk to them about the compile time situation, the response that I usually get is something along the lines of, here's why it's really hard to make it faster. When I talk to Zig people about compile times, it's the exact opposite. They're like, I'm so sorry that it's not already as fast as the hardware could possibly make it be. Here's what we're working really, really hard on making it be that, whatever your hardware is, we're using it to the maximum extent to give you the absolute lightning fast compile times. The attitude difference is just totally night and day. And this was something that I picked up on ever since I met Andrew Kelly, who created Zig, at a conference, is just there's this big attitude difference in terms of how important compile times are to the roadmap. Every year I fill out the State of Rust survey, and I'm outing myself. Whenever somebody reads that, they can tell if it's me. Even if I didn't put my name on it. Like they ask about, oh, do you want this feature? Do you want that thing stabilized? Do you want this? That? Every year I'm just like, I don't care. Just make it faster. All I care is compile times. I don't care if this gets stabilized or that gets stabilized or this is available in language. Everything in Rust is already, like, from a feature perspective, fine. Like all these little, like, oh, what if you have like async functions? I'm like, I don't care. I'll just put them in the block. It's fine. Like I make an async block at a closure. It's like, I don't care. I just care about, I want the compile times to be a lot lower than they are. But of course, I don't seem to be in the majority on that in terms of Rust users either. It seems like, to be totally honest, a lot of Rust users are okay with the compile times being the way they are. And maybe that's because they're working on smaller code bases. I don't know. Or maybe it's because they're coming from like a Java or a C++ background, and they're like, what's the problem? But coming from an Elm background and also now, having experienced like Zig compile times, I'm like, I can't not be bothered by it a lot, all the time, like knowing what's possible. So yeah, I don't know. I've ranted on my podcast, which is Software Unscripted, by the way, a lot about Rust compile times. We were thinking about a rewrite anyway. I don't know that if we would have like seriously discussed doing it in Zig if Rust compile times are fast. I think we would have just been like, no, we're going to rewrite, but we're going to rewrite it in Rust again.
Okay. I'm probably in the camp where compile times are not that big of a problem for me nowadays. It used to be a problem, and then two things happened. First, modern ARM hardware is pretty decent at compiling Rust. So you have M4, and it's much better than it used to be. And the other part was the Rust compiler did actually get faster since 1.0. I hear that a lot from people that come from functional programming and from game dev.
Hmm.
for people that need fast feedback loops, because this is kind of a development model that doesn't really fit well or perfectly well right now with Rust. I feel
Yeah.
like if I were to write a game from scratch, I would also be cautious to maybe use Rust or not. I wouldn't be sure, but is that true? Like, does that ring true to you where you say it's because of your background? Maybe even before using Rust, you learned that there's a different way to build software.
I certainly think that it's the degree to which compile times bother you would depend sort of obviously on what you're used to and what you, I don't know, think of as sort of possible or normal. Like if I'm used to Elm and like, sub-second, recompiles and stuff like that, then yeah, I mean, it's going to bother me when I'm waiting 10 seconds, to be able to build my thing or to run my tests. Similarly, I mean, like at Zed, it's just really obvious. Like the classic example of the the really obvious pain point here is I'm like, I just need to scoot this thing over by 2 pixels because it's a little bit off. I just need to make a little tweak here. And I'm just sitting there waiting for that. I'm like, if I were using a browser, JavaScript or something like that, I wouldn't even need to, think about this. I would just be like, refresh the page. Now, granted, in modern front end development, a lot of people have like TypeScript and Next.js and this and that, but those are self-inflicted wounds. You have the option to not do that to yourself. In Rust, there is no such option, as far as I'm aware. Like, there's no way to say I have this big Rust code base. I'm just making this small tweak to this one thing. I think if you wanted to do something like that, you would probably need to, I don't know, do something like reorganize, like really aggressively reorganize your crates in a way where you can try to just make it so that the caching works out or something like that. I mean, we've tried to do some of that at Zed, obviously, because compile times are such a pain point. But yeah, if you need to make a change to something deep in the bowels of our code base, it's always going to be super slow. Something that's dependent on by lots of things. There's just no way to get it to be fast. Whereas again, like if you have a giant JavaScript code base, not TypeScript, where you have to do the builds and everything, but just have a giant vanilla JavaScript code base, obviously that has its own problems on many, many levels. But in terms of feedback loop, it's still just going to be very fast. And yeah, so if that's the type of thing that you're used to, is this sort of JavaScript or Elm like feedback loop, it's just very frustrating and innately, I think, to work on a large Rust code base and to have these slow feedback loops.
Yeah. Zed has sort of their own UI framework as far as I remember, but there are systems like Dioxus and Leptos now that have hot reloading, and it's an experimental feature, but they somehow made it work such that you can make certain modifications in your code, and it's kind of guarded by certain way to write things. Not everything is hot reloadable, but some components are. But of course, you're not writing some sort of user interface with Rock. You're writing a compiler, so that's completely different, right?
Yeah.
And I can see how that might be frustrating, where you make a single line change and then you wait for 30 seconds for a clean build and so on. So that can certainly be true. Have you considered any alternatives, other languages that maybe have faster compile times but are not maybe that much of a paradigm shift? Like maybe, I don't know, Microsoft, for example, they rewrote C# in Rust, but also TypeScript in Go. Or there might be, actually TypeScript and C# might also be alternatives. I don't know if you want to write a compiler in TypeScript necessarily, but perhaps C#, I don't know. Or have you considered any other languages other than SIG as well for the rewrite?
Well, this gets back to the performance ceiling, right? So, like I said, it's been a hard, non-negotiable goal that the Rock's compiler needs to be as fast as possible. It needs to be really, really fast. It needs to not just be like kind of fast. It needs to be extremely, extremely fast. That's a really, really important thing to me about the compiler, which means that any language of the garbage collector, immediately out. So Go, immediately out. C#, all of them, no dice. So really, I mean, the only contenders I would say would be like Rust, Zig, or some other language that basically supports memory unsafety. So even like when we got very far into the Rust compiler, like the Rust implementation of the Rock compiler, we were using unsafe more and more, and using it in the Rusty way where you try to like minimize the blast radius, but to do things like structive arrays and whatnot. And I don't know, maybe we should get into that, but yeah, like there is like, even though like, so Rock also has a goal of being for a language that automatically manages memory for you and guarantees memory safety. It tries to be very, very fast. And like I said, like, we want like run faster than Go is a goal. One of the things that makes me realize is just how important memory unsafety is to performance. Like basically, there are some things that you cannot do or cannot do ergonomically if you have a hard requirement of like memory safety is enforced. There are just some things that require memory unsafety if you want them to go fast, because in order to enforce memory safety, you have to do runtime checks. So a really, really easy example of this is bounds checks. So sometimes the compiler can elide this, but sometimes they can't. Like the way that Rust gets memory safety around buffer overruns is just that, if you have a slice or you have a vec and you do like an access at a particular point in there, that's going to be checked at runtime. And if you do like the square brackets, then it's going to panic if you have an index out of bounds. Or if you do like a .get, then it's going to give you back an option. Then you have to handle, what if it was in bounds? What if it was out of bounds? C does not have that. And of course, Rust does have the unsafe equivalent of that, but then you have to wrap it in unsafe and then you avoid the bounds check. Well, the point is that if you want maximum performance, you don't want that bounds check. You want to just not do that. And the downside is if you make a mistake, then now you have undefined behavior. So obviously there's a trade-off there. But in a language like Rock, we don't offer the unsafe option. Like even if you're in like the hottest of hot loops and you're like, no, I can, the compiler is not able to elide this bounds check, and the bounds check is actually causing problems for me in practice somehow, you're stuck. You just like, sorry, we don't support that. And so the performance ceiling on something like Rust or C, because Rust does allow you the option to say no, you can do it without the bounds check if you're really, really sure. C just doesn't have the bounds check in the first place, and Zig, much like Rust, has the option of you can do it with or without the bounds check. Zig actually will do it with like so you can, when you're compiling, Zig has different optimization levels, one of which is optimize safe, which is basically like what Rust does. So it's like always have the bounds check. You can also have optimize fast, which basically means we'll do the bounds check in debug builds, but in release builds, we will not do it. Kind of similar to how Rust will do panic on overflow in debug builds, but then in release builds, it'll just let the number overflow and just the integer just wraps around. Zig does that same thing for like memory access. If you compile with release fast as opposed to release safe will just keep them. So basically, those types of things are not accessible in a language like C# or something like that, unless you want to drop into CFFI. And at that point, I'm like, well, if I'm going to do FFI, why don't I just write it in one language? So that's the type of thing that I see as sort of a reason that we did not consider languages like C# or Go, even though they are plenty fast for garbage collected languages. However fast they might be, I want that maximum performance ceiling to be available.
One of the killer features that keeps coming up in every single discussion I have with people that compares Zig and Rust, which are fundamentally two different languages, is that Zig has this very nice concept of comp time. And in Rust, we have not so much. We have derives, we have a build.rs, and we have, macro rules, but that's more or less what we can do. So from your perspective, knowing both concepts, what is your current feeling about comp time? Is it something that Rust should add, or is it something that is very much native to Zig and the way Zig works, and there are better alternatives in Rust?
I don't think you could retrofit comp time onto Rust. I don't think that would make sense. The thing that's really cool about the way that Zig uses comp time primarily, I would say, is that Zig has comp time instead of a whole laundry list of features that Rust has to try to do the same kind of job. So you'll learn this one concept, and I mean, there's some different aspects to the concept. It's not like it's this, here's comp time. It runs at compile time, the end. There's a whole like supporting ecosystem around that. Like, okay, if I want to do type introspection, that's just like a thing I can do at compile time, but you do actually have to go learn like how the type introspection stuff works. Kind of like how in Rust, you have to go learn proc macros, though proc macros are a lot more complicated than comp time, which I would say is the other nice thing about comp time. It's not just that it's one powerful feature that takes the place of several other features in Rust, but also that it is conceptually pretty simple. The learning curve is not as high as something like, again, I'll pick on proc macros. That said, I don't want to say that it's all upside and no downside. I mean, one of the things that is thing that I miss from Rust when I'm working in Zig is that because Rust has like full parametric polymorphism, including of arguments, Rust types tend to be more self-descriptive than Zig types are. That's like pretty common in Zig to see something where at the type annotation level, it says something like, oh, this takes an any type. Now, this is not the same thing as like in TypeScript, for example, where you have a type called any. It's just this magical thing that like, you can give it anything and it's all going to work out unless it crashes at runtime or gives you horrible things. That's not what it means. What it means is just that this is something that's going to be resolved. Like this type is going to be resolved at compile time rather than being like fixed to a hard-coded type that you've written down. So you will still get a compiler error if you misuse that function. You try to give it a like incompatible type. But again, the thing that I miss from Rust is that in Rust, I would be able to see a type written out. So just at a glance, I can say, what does this function take? In Zig, it's much more common than it is in Rust that in order to find out whether or not something succeeded or failed, I actually need to do a build. So the analogy here would be macros in Rust. Sometimes I have some code and I'm like, okay, I'm looking at this. And based on looking at it, I'm not totally sure if this is going to compile or not. I need to actually compile it to figure out if it's going to work or not, because it has to resolve all the macro stuff. And then based on how the macros resolve, okay, maybe it's going to turn out that something did or did not compile, and then I'll get an error. So I'm still getting the error at compile time. But of course, I would prefer to just have it be more visually obvious, where I can just look at it and say, like, this is definitely going to work or this isn't going to work, without actually having to wait for the compiler to, go through the macro expansion to be able to tell whether or not it compiled. That's kind of that analogy, I think, applies to Zig's comp time as well, where there's a higher number of cases where I can't just look at it and know for sure like what its type is or what types this function accepts or doesn't accept. I have to wait for the compiler to go through and give me that feedback. So it's sort of like the absolute fastest feedback loop is I just look at it and I can tell from my intuition and my experience with the language. The second fastest feedback loop is compile time. Then the third fastest would be runtime. So there's more things in Zig that are in that second case of I can't just look at it, I have to actually run the compiler, than there are in Rust when it comes specifically to type annotations, because comp time is used in type annotations like that. So this is kind of an inside baseball thing, but I think anyone who's used both languages would pick up on that as like something like, yeah, I do appreciate the conceptual simplicity of comp time and how it can take the place of all these other language features, make the language simpler and, learning curve and all that good stuff. And it's very powerful. There's things that you can use comp time for in Zig that I guess I haven't maybe thought through it, but like it seems like it would be harder to try to wrangle all the different Rust features together to do the same thing. But that is a downside, is that you don't get, some of your type annotations are just not as self-descriptive. And in order to tell what this function takes, I either need to go read the implementation, or more likely I need to read the comments for the function that's like, okay, here's what you can give this thing, right? But I can't tell just by looking at the type annotation. I actually do need to go read some documentation just to know what I can pass to this that will compile at compile time, just like with the macro.
I'm not an expert on this, but as far as I know, Zig's comp time also takes the outer scope into consideration. If something was defined before the comp time call, then you could access that. I don't know if that is true. Maybe correct me if I'm wrong. But there is a crate called grab time now, which works for us. And it takes a piece of code and then compiles that in a separate project, and then it inserts the result into your project.
Yeah.
So it does not access the outer scope though.
But again, going back to to me, the cool part about comp time is it has something in common with functional programming, which I love about functional programming, which is the subtractive aspect. It's the thing that I most like about comp time in Zig is all the features that Zig does not have because it has comp time. Yeah. So if you add comp time to Rust, which already has all those other features, it just seems like it's moving in the wrong direction. It's like, well, no, the thing that I like is the reduced feature set, smaller set of simple primitives. Similarly to how, if you take something like JavaScript or TypeScript, you're like, oh, let me add some more functional programming stuff in there. It's like, well, no, but what I like about it is the smaller tool set. I want a smaller tool set of simple primitives. I don't want to just add yet another way to do it into, something that I think is already too complex, like in the JavaScript ecosystem.
Yeah, I can fully get behind that. And also, whenever you talk through such a technical problem or maybe a technical decision that was made, it always feels like your opinion is very balanced. You don't really take any of both sides. It's just that you pick what works best for you and for the team, right? And that's very refreshing to hear as well, because everything is like backed by facts and backed by a lot of knowledge as well. So that was pretty impressive. I guess we could talk about that for ages. Unfortunately, we did run out of time. But there's one final question that I commonly ask at the end, which is, what is your message to the Rust community?
I think the biggest thing would be focus on the end user. I think it's easy because Rust is such a big language with so many different features, and there's so many different competing concerns you can have in terms of like, I need to balance like making this safe and also making it, well tested and well structured and easy to maintain. There's all these different things that you could be thinking about, and I think focusing on what's the end user gonna get out of my program, that's the most important thing. That's got to be the North Star. And don't lose sight of that when you're thinking about all these other things that you as the programmer could be thinking about. And I think that's something that Zed really embraces, which I really appreciate about Zed. It's like, we brag about things like, this is a code editor that runs like 120 frames per second when you're like scrolling through your tabs, as switching like code editors as fast as possible and things like that. And I think that's how it ought to be. It shouldn't be that we're bragging about, Zed is innately good because it's written in Rust, but rather that Zed is really, really fast, and writing it in Rust is the way that we achieve that.
That was pretty amazing. Richard, thanks so much for taking the time. Where can people learn more about Rock?
Yeah, so Rock, it's R-O-C. It's named after the mythical bird, not the rock, like the inanimate object, or the genre of music. So roc-lang.org. Like I said, we're in the middle of a compiler rewrite, so you can definitely try it out, but stay tuned. I would say this is going to come out, I'm assuming, somewhat before Advent of Code 2025, but we're hoping to have the new compiler ready to rock for, pun actually retroactively intended, ready to rock for Advent of Code 2025 so people can try it out. And so far, we're on track to be able to do that. But yeah, there's going to be a lot of new design changes and awesome stuff for the language. It's going to be easier to get into, especially for beginners. And people can look forward to all that. But if you want to get involved sooner than that, or certainly if you want to contribute to the compiler or donate to what we're doing, we have a nonprofit foundation set up that people can donate through. So it's tax exempt in the US. And all of that is at rocklang.org. And of course, if you want to follow any of the Rust stuff I'm doing, check out Zed, zed.dev. It's been my daily driver editor for years now. I love it. And it's been just getting better and better.
Yeah, that was amazing. Greetings also to Konrad Erwin and Volker de Vries, who used to be guests, as you mentioned. Richard, thanks so much for taking the time.
Thank you.
Rust in Production is a podcast by Corrode. It is hosted by me, Matthias Endler, and produced by Simon Brüggen. For show notes, transcripts, and to learn more about how we can help your company make the most of Rust, visit corrode.dev. Thanks for listening to Rust in Production.